nicely given by Werner. He will tell us about, well, it's a different title.
Just one word.
Towards QC correctly.
All right, yeah, as you can see, I changed the title slightly just because I think we are in the process of getting there, but we haven't quite reached our goal yet. Really getting complete set of QC corrections for single spin observables. So I'll tell you, our efforts, I'll tell you about our achievements and also the problems that we still have. And this will be a fairly technical talk towards the end, so I'm really going to go down to some of the nitty-gritty of the calculation. So bear with me if you're interested. So I'll focus on this kind of process where you have single inclusive production of, say, hadrons or jets in a lepton-proton scattering. I'll tell you why I'm using that process. It's not going to be the prime focus of experimental efforts in the future, maybe in the IC, but it's going to be, it's a good tool theoretically to address these things that I'm interested in. I'll briefly tell you about an extreme order calculation that we've been doing for the cross-section for that, for the unpolarized cross-section. It's really, in some sense, a very simple, comparably simple calculation. That is work that Patrick's and Mark and I have done. Patrick is a former student of mine who in the meantime graduated and went on to do different things in his life. So he has been really instrumental in these kinds of calculations that I'm presenting today. And then I'll spend more time on our efforts to compute QC corrections for the single spin symmetry A sub n for this process. And again, this has been done with Patrick, but also with Yuji Koike in Japan. And I've had very valuable discussions with John Wei. We will hope to continue that here. Okay, so motivation, why am I looking at such processes? Of course, the motivation is simply that we care about this because of the large single spin asymmetries that have been observed for the related proton-proton process. You all know about this. I don't have to go into any detail about that, but for example, here at RIC, Star and Phoenix have seen, like in previous fixed target experiments, large single spin asymmetries as functions of Feynman XF. And clearly that's, as we heard yesterday from Daniel, that's really a very important part of our transverse spin physics field. And in some sense, this process here with a lepton instead of an incoming proton, and of course the other one polarized then, is really a simpler process to look at and to still have access some of the same physics in some sense. So as we know, these single spin asymmetries for such processes, for single inclusive ones, are what we call power suppressed in QCD, higher twist in some sense. As you know, over the past 2-3 decades, various mechanisms have been discussed. Clearly, these are processes, there's a single hard scale PT that should be formulated in terms of collinear factorization. That's really what we use here. And as it was found by John Wei and George many, many years ago, these processes can be formulated theoretically in terms of twist-free matrix elements in proton, but also in the fragmentation process. And Danny gave a nice overview about that yesterday, and we really took it quite far now when we start to do global analysis of reaction data in terms of such matrix elements. If you look at proton-proton scattering, of course, there's a wealth of contributions even at the lowest order, as we also heard yesterday. There's Sivers-type contributions with 3 proton matrix elements. There are fragmentation-type contributions. That already makes it complicated. You have also gluonic correlation functions and all that. So there's much more going on than we usually have in, say, the unpolarized cross-section for such a process. All studies that have been done so far have been done at lowest order in perturbation theory, because that's already in some sense difficult enough. And none of the calculations have so far, at least in the phenomenology, have used any proper evolution. So we have in fact mimicked evolution by using that of the unpolarized particle distributions for the twist-free matrix elements, which is a simple approximation. You can do a little bit done now by now, but still that hasn't been done yet properly. Now, this process here, which I'm looking at today, has been brought forward a long time ago by Mauro and Lena and also by the collaborators almost 20 years ago. The nice thing about it, you can choose basically if you want the same kinematics as in PP, whether that's experimentally doable or relevant is a separate issue, but at least in the theoretical calculation you can do that. And certainly, just because there's an initial lepton, this process will be simpler. You will have generically fewer, contributions, fewer sub-processes. If you do it with a jet instead of a hadron, in fact, you want to have a fragmentation component, which is maybe something that makes it even simpler. As such, we can hope that by analyzing this process, we can shed light on the role of mechanisms for proton-proton case that we are more interested in. But more importantly, from at least for my purposes, a simpler process may serve as a template if you want to go beyond leading order. If you want to, especially address the role of QCD corrections. Right? You don't want to start with full complexity of BP. You would like to start with something simpler. That's what we try to do. Okay, and I should clearly mention that, of course, it's not something. And going to NLO is not something that is a tiny correction that is academically interesting but not so important. It is really important, right? For example, this is a calculation we did with Andreas and Daniel de Florian and Melanie Fulfer years ago, where we look at IPT production of hadrons in the compass, and this shows leading order, next leading order, and then we do a resum calculation. And you see, just by looking at the lower two lines, how large the next leading order corrections for such processes can be. And they will be even larger for PP scheduling. This has, of course, also been investigated for the cross sections. And it's certainly, in some sense, a dangerous thing to analyze data like A sub n, as we saw them earlier here, in terms of leading order alone. There will be large corrections in the numerator and the denominator of this symmetry. They might cancel, which would be great. I doubt that will happen too much, but anyway, it's dangerous, of course, in some sense, to do it in leading order, and we have to go beyond. Okay. Yeah. This was IPT CDIS. You will see results soon for single inclusive, but it's generic. I mean, it will happen. Also in PP scheduling, for instance, and also in single inclusive.
Could you give me a sense of why the resummation contributions can get larger for higher PT?
Yes, the resummation effects come from something we call platonic threshold, when the incoming partons have just enough energy to produce the final state. And the higher you go in PT at a given center of mass energy, the closer you come to that platonic threshold. And then the logarithms that resummation addresses, they just become more important. That's exactly what happens. Okay, so very briefly, I'm going to give you some idea about NLO calculation for the spin average cross section. That's really a very standard calculation. It's in some sense a very simple calculation. I use that also to introduce some notation that we will need for the single spin case. I should mention that half a year after we've done that calculation, that was already pushed to next leading order, which is kind of amazing, by Frank Petriello and Xiaohui Liu and collaborators for the case of jets produced in electron-proton scattering. So it's very rare that once you do an NLO calculation, half a year later you have an NLO calculation, which takes 2 decades. And nowadays these things go fairly quickly. So that's kind of encouraging. But I'm going to stay with next leading order simply because we do the calculation completely analytically, whereas this, of course, has to be based on numerical Monte Carlo integrations. And so this will be valuable for developing all the tools that we will need for the single spin case as well. So here's leading order, or here's the generic process, first of all. So we have an incoming parton from the proton, we have an outgoing parton C fragmenting, and we have the lepton line. For my purposes, for this talk, the lepton line will be always the lower line in some sense. So usually we have the lepton scattering on the top, the left at the bottom all the time, okay? So that's what we're looking at, and of course the cross-section for producing the hadron is going to be a convolution of parton distribution functions, fragmentation functions, and partonic hard scattering cross-sections for parton A hitting lepton L, producing the final state parton. Note that since we are completely single inclusive, the phase space of all these particles is completely integrated over maybe perturbative calculation. So we're only looking at partons A, C, and L. And using only these three partons A, C, and L, you basically have three Mandelstam variables, which is the center of mass energy of the incoming partons, the momentum transfer from A to C, or the one from C to L. And these are the three, in some sense, observed Mandelstam variables. And you can use those to formulate basically two kinematic variables that are relevant for describing such a single inclusive process. They're customarily denoted by V and W. The Platonic cross-section will be differential in V and W, and that's all the information we need. Everything else that would be happening here in the final state will be completely integrated over phase space. That's the nature of a single inclusive cross-section. Okay? Just keep in mind these V's and W's will reappear later. The lowest order, of course, U and T and S add up to 0, and so W will be 1. We'll see that in a second. Here's the lowest order. The lowest order, you only have the Platonic cross-section for Q lepton scattering. If you observe the hadron at high PT, then this will always have large virtuality of the photon. So the order is sort of a well-defined object by this cross-section. And indeed, as I just promised you, the cross-section differential in V and W will be a delta function in W. It's going to be delta 1 minus W simply because of S plus T plus U equating 0. And then there's a non-trivial dependence on the angle, which is embodied in this factor depending on V. V, as you know, was the ratio basically of Mandelstam T over S. Okay? So that's the cross-section we have, and that's the lowest order. If you go beyond lowest order, of course, you have to radiate gluons. You have real emission diagrams, 2x3 scattering. Gluon can be radiated from either the incoming or the outgoing quark line. So that's all there is in terms of field scattering for this process. So that's why the process is so simple in some sense. Or you have a virtual diagram where you have a vertex correction here, which interferes with the Born diagram to produce the same perturbative order. If you work it all out, and I'm going to give you a couple of details in a second, then in the end you will find a next leading order contribution that is, of course, is 1 power of alpha s now, on top of the alpha squared that the overall process had. There will be contributions that are still delta functions in 1 minus W. They come from, for example, virtual corrections. And there are also these plus distributions, which are in fact related to the threshold blocks that generate, that I mentioned earlier. And so this is a technicality. This makes the cross-section integrable over W. It's a remnant of the infrared cancellation. That's pretty much standard, and these you have functions, the regular function at the end of V and W. Okay, and that's basically what we compute analytically. Once you've done that, you convolute with PDFs and the fragmentation functions to produce your cross-section.
So one virtual correction have a leading order.
Because they have leading order kinematics. Leading order kinematics already has W equals 1, and any virtual diagram cannot change that. There are, of course, additionally some new channels that open up at next leading order where gluon comes in or fragments. That's not going to be a concern right now. We computed those, of course, but they're not so important for what comes. What is important is that if you do the real emission diagrams, you have to do a 2x3 phase space integration. And here come our variables V and W again. And I'm just writing down the 3-particle phase space in dimensional regularization, which you need to use in order to obtain singularities in the calculation. And the important point is that apart from factors containing V and W, which you would expect, of course you have at next leading order, because of an additional part in the final state, you have additional integrations for a phase space. And there are basically, you can formulate it in terms of 2 angular integrations. So if you look at your 2x3 process, then these are the 3 observed partons, the incoming one, the lepton, the outgoing one. And then there are these 2 partons, which is the outgoing lepton and the radiated gluon, which are completely integrated over phase space, right? And those can be put, for example, in their West frame, which is basically like a Colin Soper frame or a Jackson frame. And you can integrate the rest of them, the components, in terms of 2 angles. And that's why you get 2 angular integrations additionally on top of what you have in V and W. And these need to be carried out. And the art of doing the NLO calculation is to be able to compute these integrals analytically, which can be done, which is fairly straightforward. Here, just 2 examples. If you have minus stem variables between, for example, K2 and P1. It will contain, for example, the angle θ1 that comes here. And if you have minus stem variable between K1 and K2, for example, you might get both of the angles. So it's just a matter of computing the full matrix element will contain these angles everywhere, and you need to integrate them out. It's difficult, but not very hard to do. The virtual correction, on the other hand, is really trivial because all that happens is this vertex here, and this vertex can be computed in perturbation theory just to the next order. It usually is just a gamma mu matrix, of course, and you just compute the NLO correction, and you're done with it, and you can use that. So basically, you can use the leading order result and just multiply by this factor. So virtual correction for the NLO cross-section is really simple. Okay, so that's the NLO calculation for the unpolarized cross-section, and that's really fairly standard. Techniques like this were developed in the 80s for treating more complicated cross-sections, in fact. Here's one, maybe two phenomenological slides that we produced in our paper. This shows the cross-section for the process at Hermes energies. And one point I want to make, of course, is the size of the NLO corrections. The dashed black is leading order, the red solid is next leading order. So you see there's really a substantial increase of the cross-section. You need to know NLO to have a good picture. The blue lines we have here, in fact, are what we call Weizsäcker-Williams contributions. As it turns out, once you go beyond lowest order, you get contributions, of course, as we saw, of this type. And they can be dominated by almost real photons that are produced or that are used in this scattering process. For a while, we were hoping that these would be completely dominating the cross-section, so that by just using these, which can be fairly easily computed, we could get a good picture of the full NLO. But it seems they only go sort of half the way, so you really need to go the full NLO correction in order to do that.
Can I ask,
Sure.
how you remove this one over time? So
Absolutely. So, right. So there are infrared divergences which cancel between real and virtual diagrams. And what's remaining is the collinear divergency, which is removed by collinear factorization. That is sparking. I'll come back to that a little later. I'm back in case of this.
And then can I ask, if these contributions with the Q square, with the low Q square photon are important, is there also contribution from this resolved photons?
Yeah, we looked at that also. A very good question. There is, it turns out to be not so super big, like 10% effect on cross section. It would be, yeah, it's possible to include that, but it's a bit tricky because once you accept that this is only part of the picture, of course you need other corrections as well. It's a little difficult to, to separate it from the rest and to say, for this one I now include a resolved component and then I add up the remaining difference. It's a little tricky, but they are there, but they're not super big, it turns out. So one of Andreas' students actually looked at that.
Maybe further.
Yes.
Since I'm sure we calculate how far you take a mass scheme to subtract all from virtual state. So if you do that consistently, that means you effectively introduce photon distribution.
That's exactly what we do. Exactly.
So you just have to parameterize in some.
Yeah, exactly. We did it in fact in two ways. We used that approach, but we also did a calculation where we basically kept the electron mass because this is regulated by the electron mass. And the results turn out to be the same. Absolutely yes. Okay, here's something for the ERC where in fact the Weizsäcker-Williams is above.
I have a naive question. Aren't there Hermes data actually?
There are data from Jefferson Lab, indeed, which I don't show here, and there are Hermes data, I believe. I'm not sure. No. Wait, there are data which are related, but they have. So the point is, you want to be really simply inclusive. The Hermes data are not entirely simply inclusive. Yes. That's the thing. Yeah. No, remember.
We also integrate all the Q.
Exactly right. I mean, that's so they have cuts on Q, which is perfectly fine. It's, it's what you usually do in lecture scheduling. You hardly ever look at this, really, right?
Data is on the spin AC.
That's right. They do that.
Not on the.
Yeah, you're right. Okay. You're right. Yeah, there's no process data. It's all the space. Okay. Let me now come to the more important part, our efforts to go to NLO for case of N. Here's again the usual picture of what the singular spin symmetry is, and as you know, as you heard also yesterday in Daniel's talk, this can be formulated in terms of these three matrix elements, which produce a phase in the hard scattering. So you pick up a phase detected, for example, a soft gluon pole on this line. There are this, as I show here, is like a twist-3 matrix element for the proton. So it's an initial state effect I'm showing here. There are, as we saw yesterday, also important replication effects, and maybe there are the dominant source of single-spin asymmetries in such processes. But that's not right now my concern. I'm interested in computing NLO calculations to such contributions, whether they eventually are the dominant source of the symmetry is the second issue. I'm just doing this as a theoretical tool. So I'm looking at QCD corrections for diagrams like this, which we need to do in order to get NLO. Okay, so let me focus on this type of phenomenon. So it's Dunway and George showed in the 80s. Was it in the 80s, 90s? 89, 90, right? What you do is a collinear expansion, so you separate the matrix element from the hard part. And what that does for you is that you introduce a, what we call now, of course, a Schusterman matrix element. It's a function of two momentum fractions defined by a suitable Fourier transform. Momentum fractions are typically defined in terms of the momentum fractions of the quarks that participate. Thank you. And then you have a hard scattering process that now has an additional gluon that attaches to the hard scattering. And what you need to do when you do the collinear expansion, you need basically to take a K-perp derivative of that matrix element, and you have to choose a certain set of kinematics that has been used many times, where this gluon comes in with a light cone plus component and also with a transverse momentum. And then you have momentum flow through the diagram, and you have to take a K-perp derivative, and in the end set K-perp to 0 in the derivative part. And when you do that, you get the hard scattering cross section. That's been done all over the place since this was invented. Now, the way this goes and the way this contributions come in single inclusive scattering is as follows. For example, here you attach that gluon to this fragmenting quark line, right? And what you have here, this piece here is a propagator, and that propagator generates your phase. You can use it to generate a phase. It will give you a delta function. So you will get a delta function that connects the two momentum fractions, x1 and x2, and a piece in K-perp. Likewise, this lepton here is unobserved, and it will be on shell. It's going to be an outgoing lepton that's on shell. So there's a delta function that puts it on shell. This delta function is simply saying delta of GL squared prime is 0. And if you work out the kinematics, you find that the delta function involves, again, one of the momentum fractions, some kinematics, and also some K-perp dependence. Right? So now you think about it, now you have to take a K-perp derivative of this contribution, which means that the K-perp derivative will act on these delta functions, because K-perp is sitting here right inside the delta functions. Right? So you need to do that, and you, of course, have K-perp also in the other places in the hard diagram. So what you need to do is, as Dunway and George showed, you need to take a K-perp derivative and set K-perp to 0. Now the fact that you have K-perp in the delta function means you take derivatives of the delta function, which by partial integration means that delta functions, that you get derivatives of the function that you have here. And in order to make that really work, what you can do is you write down your expression that you have, which is, I should have written G here, sorry. I sometimes use TF, sometimes GF. So this is the Schusterman matrix element. And this is the hard part you have. And now you have these two delta functions that contain K-perp. Turns out on the right side of the cut, you have only one delta function containing K-perp. And now you want to take the K-perp derivative and set K-perp to 0. And if you work out the details, what you find is you get two pieces. One contains a derivative of the Schusterman matrix element. The other one contains the Schusterman matrix element without derivative. Okay? So that's been pretty well established. And for single inclusive scattering, you get a derivative term. It's very widely known. You don't get it for other processes like Gluon or something. But here, for the single inclusive production, you get a derivative of the Schusterman matrix element. And if you apply this for this particular process, you do the complete leading order calculation. That's something that John Way and collaborators have done, and John Bo and Andreas. Then you have a polarized cross section in the numerator of the asymmetry, which of course is a certain arc part here, sitting here. Again, because leading order is delta function 1 minus W. And you first of all you get a derivative piece, And that's in fact something that we call a soft gluon pole, because it has the two-stoned matrix element as at the same values of x for both. So the gluon that you couple becomes soft. And that is back the contribution that Janway and George worked out in the 90s for such processes. But you also get this non-derivative piece, and the way they combine is a very simple one. They combine the fact as the difference of the two contributions. So, in other words, these two pieces we saw here, this one and this one, when the dust settles, they combine in a very simple way, like this. Okay, that's the leading order picture. It will break down beyond, but at leading order, you have this simple combination that was in fact found in a paper by Janway, Chris Novares, and Feng, and myself a while ago. And that's generic for all kinds of massless, single-inclusive scattering cross-sections. You can prove, in fact, in a more rigorous way that this combination should appear. That's something that Yuji and Tanaka have done a little later. They call it a master formula. We'll hear about that. Now, that's the leading order. Now we want to go to next leading order. There's been work on next leading order corrections for single spin asymmetries. I hope I haven't missed anybody, but this is what has been done, I think. Either on Drell-Yan, on the weighted asymmetry for Drell-Yan, or on semi-inclusive DIS. It turns out neither of them has any derivative pieces, just by kinematics, they don't appear. And that turns out to make the calculation a lot simpler, I believe, than the one we've been trying to do here. I should mention that similar things have also been addressed in terms of this for transverse momentum broadening. It's a separate issue, but again, these are contributions where no derivative pieces appear. So now I'm going to take you the last few minutes of my talk through some of the features of that we found when trying to do an NLO calculation for this particular cross-section, which has derivative pieces. So when you start doing that, first of all, you look at the real emission diagram. So we now have an extra gluon that's radiating into the final state across the cut here. And of course, you have diagrams that look pretty much like leading order plus extra gluons. For example, you have possibility to pick up a soft gluon pole here in this diagram, which is really much like what happens in lowest order. This diagram, this will have a certain color factor that comes with it. And when you do that, when you compute these things, it's pretty straightforward. The techniques are similar to what we had for the unpolarized case. You find, again, both the derivative piece and non-derivative piece. They come now in different combinations, which is kind of expected, so they don't come in a simple, nice combination anymore, but they both appear. Also, what you find is you produce dust distributions like we had them in the unpolarized case, so that's not a surprise either. Okay, so this part is, I think, pretty well understood. Yes?
Sorry, I interrupt you on something that was written in the previous slide. When you said that NLO calculations are available for the weighted asymmetries,
right.
What did you mean? You mean PT weighted? Or,
yeah.
So single spin asymmetries, PT weighted single spin asymmetries.
So Feng and I looked at this, started this and looking at a specific way of the Young cross section, which because if you don't do that, then you have something that could be addressed in terms of Silver's functions. Yeah. But once you take the weight, it all collapses into which you start with. Okay. Okay. Then we have new types of contributions that attach the gluon to the gluon that now is radiated now. And that's interesting because this gluon is still completely unobserved in the sense that the quark still fragments. And this is a gluon that will completely integrate over its phase space. And normally in the lowest order calculation, you always find that attachments to unobserved particles cancel. Here they don't. And in fact, you badly need these contributions. You pick up a soft gluon pole from these as well. The diagram comes with this color factor Ca, and it contributes double poles in epsilon. Come back to that in a second. And it contributes also a derivative piece. And the reason why these diagrams are really important is the following. This comes with Ca. The previous diagrams we saw come with Cf minus Ca over 2. These produce double poles in epsilon, which are infrared singularities. This one produces double poles in epsilon. And in the sum of these diagrams and these diagrams, the Ca part of the double poles cancels. And that's truly important because the virtual correction which we will add in the end, has double poles only coming with CF. Yeah, so you better have something that cancels the CA part with 1/epsilon², otherwise you would be completely messed up. Okay, so that works out, and these contributions are really important. I think also there's no reason why they should be 0 like they are needed. Okay, so that's the next part. So then, additionally, what you also have are so-called hard pole contributions. So far, all contributions were sitting at x1 equals x2 equals x. But there are also other pieces in the diagram where you can pick up poles. And these poles will have no longer x1 equals x2. That's why they're called hard pole contributions. And what you find when you work out, for example, a diagram like this, you find that the Schusterman matrix element is probed at x and x times 1 minus x tilde. Now, where x tilde is some kinematic factor. Soft pole contribution would have just x and x. Hard pole has an additional factor here. Now, the issue is that x tilde will depend on kinematics in the sense that it will depend on Mandelstam variables that involve, for example, this unobserved gluon. Right, so x tilde is a simple expression. It depends on a set of Mandelstam variables. The trouble is now that, of course, you want to integrate over the full phase space of that outgoing gluon because it's not observed. What you observe is the final state fragmented quark in this case. And that immediately means that you have now phase space integrals sitting inside your Schusterman matrix element. And that was in fact discovered before. Feng and I found the same issue in Young calculation. So that's not completely new. But it just becomes much more complicated here. I'll give you a little idea why this is complicated. So for example, if you have such a contribution, it comes with a hard pole diagram. K is the gluon momentum. You want to integrate over K, you want to integrate over the space space. So it's sitting right in there. One way to approach this, you can do a Taylor expansion, formal one, of this Schusterman matrix element about x, x. Right? So you start out with x, x, then you have a derivative piece, and you have a whole tower of higher derivatives, all multiplying this hard piece. Now the first two pieces, they are nice because they look like soft gluon pole contributions. And in fact, it turns out that you really, again, badly need them because you need to combine them with the other soft gluon pole contributions that we had in order to get sensible results. When I told you first that I could integrate the soft gluon pole contributions by themselves, I wasn't quite telling the truth. The thing is, it works completely only after you add these pieces. You find that the soft gluon pole by itself has inverses of squared Mandelstam variables, which are tricky to treat in dimensional regularization. Once you include these contributions, all these tricky pieces cancel. You get then something well defined. Okay? So you really need this contribution. And that's fine. It's easy to compute. It's kinematics independent. You can just do the phase space integral of this hard part. But now we have the rest, which contains the kinematics factor. So let's look at this a little bit. We have it here again. Just reshuffling stuff, you can pull the x tilde, which is the kinematics dependent piece, into the phase space. And the fact that you have this x tilde here turns out, you look at the kinematics, to make the integral less singular. Simply because x tilde contains the gluon momentum in the numerator. It has something hard in the denominator, but the numerator vanishes with the gluon momentum. And that simply means that certain pole terms sitting in here will just cancel. So the integral becomes a lot simpler. Of course, you need it for arbitrary n, which makes it more difficult. But what you find then, if you work it through, you find a structure of several terms. You find basically this piece here, which has again some soft gluon pole type of things. It has something that would normally be known as a soft fermion pole contribution, coming all with 1/epsilon poles. It has another piece that has a soft gluon pole type of piece. It has an interesting difference term here. It has a derivative of that difference term. All these pieces that I've written down here, f, g1, and g2, are just regular functions of d and w. They have pole terms. Okay, so they all should cancel in some sense in the end, right? Plus, you have a whole bunch of finite contributions. And it is very, very hard, at the moment anyway, to compute these finite contributions. And of course, you need them in the end. If you want to get a serious NLO result, you need them. That's what you're after, right? So to extract the finite piece from these integrals for arbitrary n and to sum it up again in some sense will be a challenge. And, it will be a really big challenge for any numerical work you will do in the end. That's one of the, I think, biggest issues that we're facing right now. But now we're happy with looking at the whole part because it is already very important and very difficult to work out. So this is the pole structure I find from this kind of contribution. And so now you can combine everything. You can combine the soft gluon piece, you can combine the soft gluon piece attaching to the outgoing gluon, you can combine all the hard pole terms that we have here. You can integrate that all over phase space. And finally, you have the full 1/epsilon squared part of the 2/3 processes. Okay? And again, the finite part is not under control at that level. I'm sure it can be done somehow. We have some ideas how to do it, but it's really at this level not understood how to do it. Okay, but let's stick with pole terms first. So what do you need to do next? You need to, as Ned was asking about, you need to now do a collinear subtraction, right? You need to do collinear factorization. How do you do that? So here's the evolution equation that was found in several papers over the about a decade ago for the true Sturman matrix element at x, which is what you need here. And though, if you look at it, what you find is, of course, a bunch of terms that looks very much like the unpolarized evolution, unpolarized splitting function. And there's an additional piece of the delta function here. There's another splitting function piece, or splitting function type piece here. And then there's a piece that looks a bit different. It has a type of splitting function here, but then it has separate arguments in the integrand, which means that the evolution equation is such as not completely closed because you need input for x not equal x2 in order to generate the evolution of x, x. Now, what we need, however, as we know, we need the evolution of the difference because this is what appears at leading order. Whenever you do a collinear subtraction, we have a leading order PDF basically multiplying a leading order cross-section to the pole term, right? So you need the evolution of this piece. That's not so hard to get because once you have the evolution of this guy, you can of course take the derivative. It's a bit tricky, but it works out well. Any type that is a regular convolution, which is this piece and this piece here, you can easily show that once you take the derivative, it's nothing but the same convolution with the derivative of the function. It's just an identity, right? You can do it in moment space, you can do it by partial integration by parts. It just works out completely. This piece, however, is different because here you have separate arguments. So you have to work a little harder. So once you do that, in the end, you find this expression for the evolution of the difference gf minus x gf prime, okay, which we need for the factorization. And now you can see a couple of interesting things. The first part is completely simple. It's a regular piece in terms of splitting functions and so forth. It has, for example, here the evolution kernel for the unpolarized PDFs with the same combination g minus d times g prime. That's fine. Here, however, you find a piece that has a difference between gf at the same and two different arguments divided by 1 minus x hat. X hat is z over x, so it will be regular here. And you have another piece that has a derivative of that. And now if you look back, what we found a little earlier when we looked at the hard contributions, this is exactly what we found here, right? Here's a difference here, here's a derivative of the difference. That's exactly what you need to cancel the poles. Right? So that gives us some confidence that we were quite right in extracting these poles. So we've done a very small part.
Yeah, maybe I misremember, but the evolution equation for GF with the different argument was also derived by Gluon.
Oh yeah, right. It is available in principle. It's just much more complex and it would a tower of contributions exactly. We need, of course, only this one here. But of course, if you want to solve this equation, you need input from different. Exactly. Okay, so this is the piece, and now finally we can combine all that, add it to the 2x3 piece, and at least look at the pole terms. It turns out that you need a substantial amount of integration by parts to make really work out. It's a long time, but then it works. So the poles at W non-equal to 1 cancel. And there's no other source of pole terms with W not being 1. So we are very happy about that. Completely works out, at least the poles cancel. Okay? We can look at the results in that case. Just a side remark, I'll finish up in a second. We found the same double plus distributions as in the unpolarized cross section, but we find it seems different pieces with 1 minus 1. 1/1 with W plus. So there will be differences in the NLO corrections for single spin and for unpolarized. However, we're not completely done yet. Well, the final task, and that's the other hurdle we're facing right now, is the virtual correction. Everything works out for W unequals to 1, but you have these endpoint contributions coming from the virtual corrections. The virtual corrections, of course, sit at W equals 1, and they need to cancel some extra poles we have, and they also need to just bring in some finite contributions. So we're looking at virtual diagrams. There are some really straightforward pieces where you have a virtual correction that you know completely well, and you pick up the pole like in the leading order setting. That's really easy to compute, and it produces almost everything we need. And it has no longer the structure, but that's okay. So it cancels poles and it's fine. However, there are diagrams that turn out to be much more tricky. That's where your gluon attaches to somewhere inside the loop. So you get a box diagram if you look closely, and you want to pick up poles inside that box diagram. And this can happen, for example, in this way. It can also happen in the CA, the gluon vertex diagram, where you pick up poles at one of these locations. It becomes really messy in a sense because, for example, you can make a choice where you put your loop momentum. For example, if you call this your loop momentum here, then this will depend on x1 and x2. This might as well. So you have different places where you can pick up poles depending on how you refer to your loop momentum. And we've worked really quite a bit on this, but it seems like really messy. So especially the CA part of this part, which is a combination of this and this diagram, doesn't seem to quite work out at this stage. And I don't think it's an indication that the whole formalism will fail. I think it goes through too far in order to fail at this point. I think it's really an indication that we're not doing this quite rightly. That we have to figure out. As I said, Patrick's my student. He worked on this really hard before he left. He did many other things, so he graduated at some point. Since he's gone, I've been, whenever I had some time and nothing else to do, which rarely happens, I've been revisiting this and keep working on this. And every time I discover something new, but so far I haven't managed to get it done. So it's kind of really interesting, and some really good things happen in these calculations, but it just doesn't go all the way through. Sorry about running really over time, but this is my conclusion. I'm not going to go into much detail. I only want to say that I think NLO corrections like this are doable, it seems, but they're really tedious. It's certainly the hardest calculation in this form I've done. And I think the numerical work will still be a major challenge. So even if we manage to cancel all poles to add all the delta functions from the virtual correction, the 2×3 part with the hard pole contribution will be really numerically a big issue. So it will be quite a while, I think, until we have really NLO corrections for even the simple process here available as we have them customarily in the unpolarized case. Okay, that's what we have to start somewhere, right? So there are all these extra contributions that we haven't even addressed so far. There will be some issue, some work. Thank you very much.
So you said you're having trouble